Hidden beneath the frozen wilderness of North America lies one of the most valuable and controversial resources on Earth. Oil sands, a thick, sticky mix of sand, clay, water, and bitumen, the raw form of petroleum that powers the modern world. Today, we'll take you inside one of the largest oil sands operations on the planet, where technology meets brute force to turn thick black tar into liquid gold, crude oil. But first, don't forget to subscribe for more mind-blowing looks inside the world's biggest industries. Oil sands, also known as tar sands, are a natural mixture of sand, clay, water, and a dense, sticky form of petroleum called bitumen. Unlike traditional oil wells, where liquid crude flows freely, the bitumen in oil sands is so thick that it barely moves at room temperature. More like cold molasses than oil. Most of America's oil sands operations take place in northern Alberta and parts of Utah, where massive open-pit mines stretch for miles. It's an extraordinary sight. Gigantic trucks the size of houses crawl along black fields of sand, scooping up thousands of tons of terry earth. Each shovelful is a mixture that contains just a few percent of usable oil, but when multiplied by millions of tons, it adds up to a staggering amount of energy. Extracting that oil is one of the most complex industrial processes ever developed. At the heart of the operation are the ultra-class mining trucks, each capable of carrying 400 tons per load. They're fed by hydraulic shovels that scoop 100 tons in a single bite. Every few minutes, a truck rumbles to the processing plant, part of a continuous 24-hour cycle. The mining area looks like something from another planet. A landscape carved by machinery into layers of black and gold. Each load of oil sand is carefully weighed and logged, feeding a supply chain that never sleeps. To minimize environmental impact, the industry now uses progressive reclamation, restoring mined land by covering it with topsoil and planting native vegetation even before the entire site is complete. It's an effort to balance energy demand with sustainability, a constant challenge in the modern world. Once the raw material reaches the processing plant, the real transformation begins. First, it's mixed with hot water, around 80 degrees Celsius, 175 degrees Fahrenheit, to separate the bitumen from sand and clay. This step, called the hot water extraction process, causes the lighter bitumen to float to the top, forming a thick froth. That froth is then treated with solvents and heated again, producing synthetic crude oil, the lifeblood of modern civilization. From there, it's piped to upgraders and refineries where it's converted into gasoline, jet fuel, diesel, and hundreds of other petroleum-based products. Incredibly, this process transforms a thick black sludge into something that powers airplanes, cars, and even electricity plants. It's a miracle of chemistry and engineering, but it comes with challenges: high energy use, greenhouse gas emissions, and the need for massive amounts of water. To address these, new technologies are emerging, including solvent-based extraction, steam-assisted gravity drainage, and carbon capture systems that could make oil sands cleaner than ever before. The oil sands industry is both a symbol of human ingenuity and a reminder of our dependence on fossil fuels. It powers economies, creates thousands of jobs, and supplies a major portion of North America's energy. But it also raises tough questions. How do we balance growth with sustainability? In America and Canada, regulations are pushing companies to reduce emissions, reclaim land faster, and use renewable power to fuel mining operations. Some new facilities are even experimenting with hydrogen-based extraction, aiming for a future where energy and environment coexist. As global demand for energy continues to rise, oil sands may play a key role in the transition era, a bridge between the old world of fossil fuels and the clean energy systems of tomorrow. From the depths of frozen Earth to the engines that move the world, oil sands represent one of humanity's most ambitious engineering feats. They show how far we'll go to extract the energy that fuels progress, and how vital innovation is to make it sustainable. If you enjoyed this deep dive into the supergiant oil sands operation, make sure to subscribe, like, and share this video. Titanium, a word that instantly sparks images of strength, lightness, and futuristic engineering. This silvery gray metal is stronger than steel, but nearly 45% lighter, resistant to corrosion, and capable of withstanding extremes of temperature and pressure. From jet engines to spacecraft, from surgical implants to smartphones, titanium has become one of the most sought-after metals on Earth. But have you ever wondered, how do we actually mine this super metal? In this episode, we'll take you on a journey deep into the world of titanium, how it's mined, processed, and transformed into the backbone of modern technology. From open-pit mines to high-tech chemical processing, from raw ore to shiny titanium ingots, you're about to witness one of the most mind-blowing processes on Earth. But before we dive in, make sure to hit that subscribe button and ring the bell, so you never miss our deep dives into the industries that shape our modern lives. Now, let's uncover the secrets of titanium mining. Titanium isn't found in its pure form in nature. Instead, it hides within mineral ores, primarily ilmenite and rutile. These minerals may not look like much, just dull black sands or reddish-brown rocks, but inside them lies one of the most valuable materials for modern technology. Discovered in the late 18th century, titanium was initially impossible to isolate in pure form. It wasn't until the 20th century that new chemical processes made it possible to produce titanium metal commercially. Since then, global demand has skyrocketed, with applications in aerospace, defense, medicine, and consumer products. The largest deposits of ilmenite and rutile are found in countries like Australia, South Africa, Canada, India, and Mozambique. Some are mined from beach sands, where centuries of erosion have concentrated heavy minerals. Others are extracted from open-pit mines, where excavators and trucks move millions of tons of earth each year. The scale is staggering. A single titanium mining operation can process tens of millions of tons of ore annually, yielding hundreds of thousands of tons of titanium feedstock. These numbers are what make titanium mining supergiant. And yet, even after extraction, titanium's journey is just beginning. Unlike iron or copper, titanium cannot be smelted easily. Its strong affinity for oxygen makes it stubborn. It resists simple refining. This is where human ingenuity comes in. Titanium mining typically begins with surface mining. Bulldozers strip away vegetation while excavators dig into mineral-rich sands or ore deposits. Giant dump trucks, each carrying up to 400 tons of material per load, haul the ore to processing plants. In coastal regions, dredge mining is often used. Enormous floating dredges suck up sand from riverbeds or lagoons, separating heavy minerals like ilmenite from lighter quartz grains. Conveyor systems then move the concentrated material for further processing. At the processing plant, the raw ore undergoes gravity separation and magnetic separation. Since ilmenite and rutile are heavy and often magnetic, they can be separated from ordinary sand using specialized equipment. After multiple stages, what remains is a concentrated mineral feedstock, rich in titanium dioxide. But here's the challenge. This isn't metallic titanium yet. This feedstock must go through intense chemical refining before it can become the shiny, strong metal we recognize. The next stage is perhaps the most fascinating, turning titanium ore into titanium sponge, a porous metallic form of titanium that can later be melted and shaped. The most widely used method is the Kroll process. Producing titanium sponge is labor-intensive and expensive. It takes about 10 tons of ore to produce just 1 ton of titanium metal. Yet the demand is so high that entire industrial plants are dedicated to this process, producing tens of thousands of tons of sponge each year. Once the sponge is made, it's melted in giant vacuum arc furnaces, forming ingots weighing up to 15 tons each. These ingots are then forged, rolled, or machined into products: jet engine components, submarine hulls, or even surgical implants. Every year, the world produces over 200,000 tons of titanium sponge, fueling industries worth hundreds of billions of dollars. Without titanium, modern aviation, space exploration, and medical technology would be unimaginable. Like all mining operations, titanium mining has environmental challenges. Coastal dredging can disrupt ecosystems, while chemical processing creates hazardous byproducts. Companies are investing in cleaner technologies, recycling titanium scrap, and developing new extraction methods to minimize impact. At the same time, research is ongoing into electrolytic refining methods, which could make titanium cheaper and greener to produce. Scientists are even exploring 3D printing with titanium powders, enabling lightweight, custom-engineered components for aerospace and medicine. Titanium's future is bright, literally shining in jet engines, rockets, and medical devices. But balancing its immense benefits with environmental stewardship remains one of the industry's biggest challenges. From black sands on distant beaches to roaring jet engines flying at the edge of space, titanium's journey is nothing short of miraculous. It is one of the strongest, lightest, and most versatile metals ever discovered, yet it hides inside some of the Earth's most ordinary-looking minerals. Through supergiant mining operations, advanced chemical processes, and the dedication of thousands of engineers and workers, titanium becomes the backbone of our modern world. And as technology pushes us further, to Mars, to deeper oceans, and to advanced medical breakthroughs, titanium will remain at the heart of progress. If you found this journey into the world of supergiant titanium mining fascinating, don't forget to hit like, subscribe, and turn on the notification bell. That way, you'll never miss our next deep dive into the industries, resources, and technologies that power our future. Thanks for watching, and stay curious. Deep beneath the earth, giant machines chew through solid rock like it's butter. Every year, millions of tons of earth are shifted to create underground highways, metro systems, and utility tunnels that keep our modern world running. This is the supergiant tunneling process, where science, engineering, and sheer power come together in one of the most mind-blowing construction feats on Earth. Before we dive in, don't forget to subscribe and turn on the notification bell so you won't miss our next journey into mega engineering wonders. Tunnels are the hidden arteries of civilization. From New York's subway lines to Switzerland's Gotthard Base Tunnel, the world's longest railway tunnel, stretching 57 kilometers, these underground passages reduce traffic congestion, connect cities, and even carry water and energy. Building above ground is often easier, but in crowded urban areas or mountainous terrain, tunneling is the only solution. And that's where the real engineering marvel begins. Before a single rock is broken, engineers spend years studying the terrain. Using seismic surveys, 3D laser scanning, and ground-penetrating radar, they map the geology down to every crack and fault line. Why? Because every rock type behaves differently. Granite is tough but stable. Clay and sand shift easily and can collapse. The right method depends entirely on what lies beneath. Only when the subsurface is fully understood does excavation begin. When it comes to tunneling on a massive scale, nothing compares to the tunnel boring machine, or TBM. Imagine a steel giant, stretching as long as 2 football fields, weighing more than 6,000 tons, and powerful enough to grind through solid granite day and night. These colossal machines are often called moles because of the way they burrow deep into the earth, creating tunnels that can stretch for dozens of kilometers. At the very front is the cutter head, a massive circular blade that can reach diameters of up to 17 meters, large enough to fit a 2-lane highway inside the finished tunnel. As it rotates, hundreds of hardened steel discs crush rock into rubble. This debris, known as muck, is immediately transported away by an internal conveyor belt system. Instead of needing trucks or carts, the TBM carries the rock out automatically, making the process smooth and continuous. But what truly makes the TBM remarkable is that it doesn't just dig, it builds the tunnel as it goes. Behind the cutter head, hydraulic arms place precast concrete segments into position, forming a perfectly round lining. Within minutes of excavation, the tunnel is reinforced, safe, and ready for decades of use. Some of the world's most famous tunnels, like the Gotthard Base Tunnel in Switzerland and the Seattle Highway Tunnel in the US, were carved by TBMs. In fact, Seattle's Bertha was one of the largest ever built, measuring 57 feet, 17.5 meters in diameter. In every sense, the TBM is not just a machine, it's an underground factory on the move, capable of excavating thousands of tons of rock every day, while simultaneously building a highway, subway, or rail corridor beneath our feet. Excavating rock on a supergiant scale is nothing short of mind-blowing. A single tunnel boring machine, or TBM, can remove up to 150,000 tons of rock every month. To put that into perspective, that's the weight of 40,000 cars being pulled out of the earth, month after month, until the tunnel is complete. The process begins at the cutter head. As the steel discs grind against solid rock, the material breaks down into fragments ranging from pebbles to fine dust. This crushed material, called muck, is funneled into conveyor belts that snake through the machine. The conveyor belts move the muck backwards at a rate of hundreds of tons per hour, ensuring the front of the TBM never slows down. Once the muck leaves the TBM, it's loaded into rail cars or massive trucks waiting deep underground. From there, it's hauled to the surface and transported to disposal sites or repurposed for other construction projects, like roadbeds or embankments. Nothing goes to waste if it can be reused. One of the biggest challenges in excavation is ground conditions. Sometimes the rock is stable granite, other times it's loose sand, clay, or even waterlogged soil. Engineers constantly monitor the geology and adjust the TBM's pressure and speed to prevent collapses or flooding. In softer ground, chemical stabilizers or even frozen soil techniques are used to keep everything safe and stable.